Okay, here we go, guys. So let's see, this will be page 75. For thermodynamics, today is March 1st, and this will be lecture 13. Let's double check.
I don't think you put a lecture number in the last one.
This is lecture 13.
I didn't put it last time?
No.
12 maybe.
Yeah, the last one was 12.
No, I have it here. No,
Oh,
yeah.
you did?
Lecture 13. Lecture 13. Okay. So, let's see. So, summary of last time. So, basically, we derived the first principle of thermodynamics for an open system, which is also called a control volume system. Okay, so I'll just go very quick. So it is this type of system, and what is characteristic about this type of system is that you have mass coming in, so mass flow coming in, mass flow coming out. So we say because of conservation of mass, you have that the total mass coming in needs to be equal to the amount of mass coming out. Okay? We say the general definition for the mass flow is rho AV, but then in thermodynamics will be more like AV over little v. So A is area, V is velocity, little v is specific volume. Alright? So if we were applying, we're considering heat or work going into that system, we do have the equation that, so let's say and neglecting kinetic and potential energy, we do have the equation Q dot plus work dot will be equal to M dot H out minus HE. Okay? Alright, so here I didn't put, but I'm missing the terms for what? For the kinetic energy and the potential energy. So let's do one example. So since I came a few minutes early, I was just looking at some problems. So I selected one over here, which I'm going to show you. This is the classical problem, I'm hoping. So let's go and solve this problem, okay? So problem 419. Okay, so again, all that I do now is part of the solution. You see that there is a figure there, but I still do a figure, no? Okay? Reason being is not to waste time, is because as you do a figure, it gives you time to properly read the problem statement and to think about it. Okay? So let's see, I've shown on figure 419. So before I even start, I'm going to do figure 419, and then I'm going to see if I'm missing anything. So it's a turbine. Has inlet here, there. So what is the function of a turbine? Remember, we did the little figure of an engine. We had the compressor, we had the combustion chamber, and then we had the turbine, no? The one that transforms all the pressure and the fuel and the burnt fuel into work. Okay? So that's why this is going to create they put it this way on the figure, but this is going to create, I'm guessing here, power or work. Okay? So this is the turbine. So let's read. As shown in figure 419, steam. So P1 here, so we know it's steam going in at 1. So we know P1 equals to 80 bars. T1 equal to 440 degrees Celsius. And the volumetric flow rate is 236 cubic meters per meter. So, as shown in figure 419, steam at 80 bars, 440 degrees Celsius, enters a turbine operating at steady state. So, if they say steady state, what does that mean? Basically, it will mean that E, remember we had a G generated for the balance equation, will be equal to 0, no? So just put it there. All right. So what do they say? 20% of the entire mass flow exists through a diameter of 0.25 meters at 60 bars and 400 degrees Celsius. So I guess that's 0.2. Yeah. So it's here 2. We know that 20%, so 0.2 of M1 exits at P2 equal 60 bar, T2 equal to 400 degrees Celsius, and the diameter D2 is 0.25 meters. The rest exit through a diameter of 1.5 meter. Okay, so with a quality factor of 90%. All right. So the rest, so this steam coming over here, exiting this way, and exiting this way. M1, M2, M3. So let's see, we know that X3 is equal to 0.9. P3 is equal to 0.7 bar. And D3 equal to 1.5 meters. Okay, so what do we need to do? Determine the velocity at each exit duct. So we need to find, so determine V1, V2, V3 in meters per second. Okay, so any question about what needs to be done? All right, so let's see what happened over here. So I'm going to need this figure. So I'm going to keep it over here. Okay, so the first thing I will do over here, even though we might not need it right away, but is, what is it? So I will say, we say that the amount of mass coming inside the system needs to be equal to the amount coming out of the system, no? So what is our system over here? If I needed to sketch it. this is our open system or control volume. All right? So I can just say conservation of mass flow or mass means the amount of mass coming in needs to be equal to the amount of mass coming out, no? So what does that mean? M1 needs to be equal to what? M2 plus M3, no? Yeah? Okay, I'm sure we're going to need that one later on, but for now, I always try to, do the problems the same way. So, let's see. First thing we need to do is find V1. So what can we do in order to find V1? What is the definition of the mass flow? So what do we know? Mass flow M, so M1 should be equal to what? Okay, rho AV, but we say that's not a definition really used in thermodynamics, is what? So it would be AV1 divided by V1, no? Okay, so what do we know at state 1? We know is, but we know is steam, no? So we know also the properties P1 and T1. So what could we do? We could go to the tables and find what is the specific volume for the steam, no? So I don't know, what would that be? Table A4 probably. So let's see. So let's see. We know it's steam, so I'm going to the superheated tables. What is the pressure is 80, and we see the saturation temperature is 295, and the temperature we have over here is 440. So 80, 440, what is V1? Is the first column, should be 0.03742, no? So let's see, table A4 at P equals 80 and T equals 440. We get V1 equal to 0.03742. So am I missing anything of this problem? Okay, so the truth, I still don't know how to find V1. So I know how to find M1. So M1 would be equal to what? AV1 over the specific volume, which is equal to what? So AV1 was given to us as 236. My blue is dying. Oh, I have a new color here, so let's see. Let's see if this one is thin or thick. So units for these are cubic meters per minute. And this one are what, 0.03742. What should be the units for this? Per kilogram. So that gives us what? $6,307. Okay. And this should be kilograms per minute, which might be okay, but I think maybe we might have to switch that to seconds. So that would be what? 1 minute is 60 seconds. So what would be the result then? If you divide this 6,307 by 60, 105. The reason is because they ask us the velocities are in meters per second, no? So I think we're going to need that. I don't know. I still don't know how to find B. So we got the area now. So that's what I'm just thinking. Okay. So I don't know how to find V yet. So let's keep going and see if at the end we can find something. So now we know what? That M2 is 0.2 M1, no? So that would mean then that M2 is equal to what? What would be 20% of 105? 21, yes. Would be 21, that's easy. Kilograms per second. And now, what I can say is that using the star equation, what does that mean? That we have M3 will be equal to what? I mean, is logical. If we had 100% going through M1, we have 20% leaving by 2. How much needs to leave by M3? 80%. So let's see, M3 will be equal to what? 105 minus 21 will be equal to 84. Kilograms per second. Okay, so grab an extra piece of paper here. Okay, so be honest with you, I still don't know how to find V1, but I think I know how to find V2, no?
It only asks for the exiting, like it only asks for the exiting volumes, right?
Volumes or velocities? I thought it was asking for the velocities.
Yeah, but it just only asks for the exiting, so that
Oh,
it
that's
can
probably
find
why
those
then.
two.
So you see?
I believe so.
Okay, so let's check. I know that was page 220. I cannot remember that one. So let's see. Was the problem 419? So not 220. So determine the velocity at each exit. Okay, that's true. So for V2 and V3. So you see, I wasn't careful reading the problem, no?
We have V2 and V3, we can find V1.
I think we can still find it at the end, but I don't think we can find it initially. I think all the way at the end we should be able to find it.
Yeah.
Okay? But let's go for V2 now. So, and this was 993. So, okay, since we have this figure, all right, now we're going to look at what's happening here at 2, no? So first, what is the state of the water at 2? I think it's still going to be steam, but what is the pressure? Pressure is 60, no? Temperature 400. So, completely wrong with the table. So, oh no, maybe 83, so we need 84. And this is English unit, so you see I was completely off with the...
It should be around 9.
So let's see, if the pressure is 60, we can use this one. What is the saturation temperature? 275, no? But the temperature we have is 400. So what does that mean? State 2 is still superheated, no? So what would be V2 for in this case? 0.04739. So 0.04739. Okay. So basically we can say so V2 is still V1 is still unknown. So let's say V2. Okay. Table A4 at P equals 60 and T equal 400, we had V2 equal to 0.047 4739. Okay, so now what can we do? We can use the same equation as before, which is what? The mass flow at 2 is equal to what? A V2 divided by specific volume at 2, no? Okay? So in this case, we know M, the mass flow at 2, we know V2. Then what is the area? Pi D squared, we have D1, D2. So D2 squared over 4, no? Yeah, if we use the radius, will be pi r squared. If you use diameter, will be pi over 4 d2 to the square. So this one is way too thick, so I know won't be able to read anything, but my blue is dying. So this will give us what? M2 or V2. Sorry. V2 will be equal to what? M dot times V2 divided by A, so this would be equal to what? 4 M2 V2 divided by pi D over 2 squared. Yeah? Okay, so if we do the numerical application, what do we have? V2 will be equal to what? 4 times M2 was equal to what? 21 kilogram seconds times V2, which is equal to what? We just find that one. 0.04739. What are the units? cubic meters kilograms. Divided by pi times what? 0.25 square, and the units will be what? Meter square. So I'll let you do the calculation, but the only thing I'm going to check here is the units. So the kilograms go away, and this one becomes meters, no?
Yes.
Seconds, so the units are correct. 20.3, is it check? Huh. So 20.3. So guys, you see that there is no way, I mean, we are not moving away from using the tables, no? So now we can probably do something similar with 3, but what happened with state 3 is a mixture, no? So we're gonna have to deal with those V fluid and V gas, no? V liquid and V gas. So correct, but basically we need to go to table A2, no? The table is the A3 the one with the pressure? Yeah, the one is one with temperatures, one with pressure, no?
Yes, A3 is pressure.
A3 is pressure. Okay, so that's what I was just trying to think about it. So table, here we go. Then A3, all right, is the one with the pressures. So what is the pressure? 0.7 bars. So I hope we have that one. Yes. So at so from table A3, 7 bars, what do we have? V fluid is 1.0360 times what? To a negative 10 to the minus 3. And V gas would be 2.365, no? All right, so let's say V3. Table A3 at P equals 0.7. We have V fluid equal to 1.036 10 to the minus 3. V gas equal to 2.365. So let me close this one. So you see, basically that's what I just wrote over here. All right. And what else do we know? X3 is okay, 0.9 or 90%. So that would mean what? V3 will be equal to what? Plus X3 V gas minus V fluid, okay? By now, I'll let you do the numerical substitution, all right, and you give me V3. Can somebody double check? .1286 if you want. This should be cubic meters per kilogram. Okay, so again, what do? We also know the diameter, no, for that one. So we can do the same thing, exactly the same thing as we did before. So we can say that M3 equal to A V3 divided by specific volume 3, where A equals pi over 4 d3 squared. So that gives us what? V3 will be equal to m dot m3 V3 divided by A, so that gives you 4 m3 V3 divided by pi d3 squared.
And my thing on homework or test, if we've already done like that math on the one before, it's like how we already found the equation on V2, could we just say V3 equals the equation? Or do
Yeah,
you want us to like rewrite everything out again?
You could do it because you already showed it once, but yeah, well, that's it. But if I do it again, it's because I try to repeat all the time the same process. But if you had an exam and you did it once and then you put on the second one, okay, I will see that you understood the first time. Or you can say, following a similar procedure, MV3 is whatever that equation. Okay? So if you do a numerical application, what do you get?
101.2.
101, so 101.2. And this should be, yes, that's it. Missing something? I want to see if we could have solved for V1. No, because we have two unknowns.
Yeah,
We don't know A and we don't know V1, so we cannot solve for V1, okay? Okay, so there is no V1. Alright, so let's see maybe another problem. How did I go from, oh, no, it's fine, so 75, 76. $77. $78. Okay, so let's see, we can find another problem. Oops, so, all right. Chapter 4, I like all these ones. I like that one. I like the ones we figure, so. But I don't want to do the jump. What was this one? 490, I don't want to go to 4. We can find something in the middle. Oh, these ones are good, Johnny. But I think they're about the same. So let's do this one. I don't know. Okay. So let's see. Do we have time to do this one? Okay, let's do this one. 475. Okay? All right, so there we go. $475. All right, so whatever that figure there is, generally this is an air conditioning system. Okay, so let's say it's a heat exchanger. So I do the figure. So we have this rectangular. Then what do we have? We have a pipe. Okay, I didn't do a good job, but it doesn't matter. So this is a pipe. So on that, here we have a fluid. I'm going to do that one in green. We have 3, 4. So we have refrigerant 134A, which is entering at a pressure of 5 bar with a quality factor of 0.2 and is leaving at a pressure of 5 bar with a temperature of 20 degrees Celsius. Okay? So imagine this pipe is subjected here to some air that is going in at 1 bar. So basically it's 1 atmosphere. So that's surrounding. T1 equal to 32 degrees Celsius, I guess 305 Kelvin. And we know that AV1 is equal to 50 cubic meters per minute. Okay, and that will be state 1. And then state 2 over here. I'm sure there's something, but I cannot read it. P2 equals 0.95. T2 equal to 22 degrees Celsius or 295 Kelvin. So let me know when you are done doing the figure. So let's see. An air conditioning system shown in the figure 475 in which air flows over tubes carrying refrigerant 134. Air enters with a volumetric flow rate of 50 at 32 degrees Celsius, 1 bar, and exit at 22, 0.95. Refrigerant enters the tube at 5 bars with a quality factor of 20 and exit at 5 at a temperature of 20. So no additional information. Ignoring heat transfer at the outer surface of the air conditioning and neglecting kinetic and potential energy effects determined. So basically we can add over here neglect potential energy, neglect kinetic energy, and what they're trying to say is that imagine this system is insulated, okay? It's not absorbing heat from anywhere. So they ask us to find the mass flow rate of the refrigerant. So what would that be? We need to find M3, no? Okay, or M4 will be the same, no? M3 equal M4. So So we can write this. Yeah, okay, I write it. So let me write over here. We have M3 should be equal to M4, should be equal, let's say, M of the refrigerant, no? Which is what we need to find. And what is the other thing we need to find? The rate of heat transfer in kilojoules. So this needs to be in kilograms minute. So part A. Part B, the rate of heat transfer. So we need to find Q between air and refrigerant. Okay. Kilojoules per minute. Between air and refrigerant. Okay. Okay, so before I remove the figure, because nicer here, do you have any doubt about what needs to be done? Do you understand the problem? Okay, that's the important part. If you don't understand the problem, there is no way to solve it. All right. The mass flow rate of refrigerant. I don't really see now how to solve for the mass flow of refrigerant at once. Yeah, we can start by the air, but that's not going to give us the one of the refrigerant. All right, what is this problem number? 475. Let me see 1 second. See if. Got it. Oh, yeah, I think I know how to do it now. Air and refrigerant. Okay, yeah, sorry, I should have known that. Trying to do that once. Okay, yeah, my mistake. All right, so the thing over here is that we're going to consider this as our system, as our open system, okay? All right, so now we're going to apply the energy balance or the first principle of thermodynamics. So applying first principle of thermodynamics or energy balance. To system, what do we have? So do you remember, generally on the one of the class notes, I did over here a Q and a work, no? Do we have any Q coming inside in this one? In this system, do we have any Q? Let me do maybe this one for in this case. Yeah? So what type of energy is coming in? I'm going to do this in orange, okay? Because it's going to be... So what type... Under which form is the energy going to come in? So we can have, let's say, if we start by the air, we have energy coming with the air, no? Do we have any Q? No. So we have Q0, no? In here, Q is 0. And is it any work done on that system? No, it's 0, no? Yeah, so we have here Q dot plus work 0. That equation, these two terms are 0. Now, what type of energy can be coming in? If we neglect kinetic and potential energy, the other form to bring the energy will be what? Internal energy plus work done by the pressure, which is enthalpy. Okay? So we have at 1, what do we have? We have mass of air, so let's call it some A, okay, at 1, and that will come with what type of enthalpy? H1, correct? Then what else is coming inside that system? You see, everything is coming from the figure. So this is coming in. What else is coming? We have refrigerant coming in, no? Yeah? With what enthalpy? H3. Okay? Do we have anything else coming in inside that system? No? So now we have energy coming out of where? 2 and 4. So 2 is still air coming out with H2 plus M refrigerant times what? H4. Okay, and I'm going to put over here. So I know it's not going to be very clear, guys, but I guess you can recognize here easily that M1 equal M2 equal mass flow of air, no? Yeah? Okay, so now from that equation, what can we do? I can combine the terms, so we have mass of air will be equal to what? H1 minus H2, and mass of refrigerant will be M dot sub R H4 minus H3. So what do we need to solve for over here? Mass flow of refrigerant. So mass flow of refrigerant will be equal to the mass flow of the air times H1 minus H2 divided by H4 minus H3. Okay, I'm going to stop here for a minute. Look at it and let me know if you have any question. Do you understand what we did? Okay, so now we understand why they give us AV1, because how can we find the mass flow of the air? We can go to step 1. What can we say? M of A will be equal to M of what? 1, no? Which is equal to what? A V1 divided by V sub 1. Now, can we find V sub 1 from the tables? Do we have tables for air? We should have tables for air. It doesn't matter, otherwise we can find another way. It's fine, even if we don't need it. Okay? Air is what? It's an ideal gas, no? Okay? So what is the equation for ideal gases? Remember that equation we started at the beginning? PV equal RT, no? What I need to find out is it R bar or no R bar? That needs to be equal to the universal gas divided by the molar mass. But I don't know if that they call it R bar or no R bar.
This R bar is the universal gas constant by itself.
R bar is the universal gas constant by itself, so I think this is R then. Okay? So in this case, okay. So if we do this, when that means what? That V will be equal to what? R T divided by P. Okay? So we can say here that mass flow of air will be equal to what? P1 AP1 divided by R T1. Okay? All right, so let's look at the units. So in that equation, where, let's see, AV1 is given to us is equal to what? 50 cubic meters per minute. What else is given to us? T1 is equal to 305 Kelvin. All right, so now we need P1 is also given to us equal to what? 1 bar. We need to transform that into what? Pascals, no? So how many pascals would that be? So is 1 bar is 100 kilopascals. Okay, so now do we want to transform kilopascal? Pascals will be 1. So it should be 1 is not double point, okay? So 1 10 to the 5 Pascal, no? Okay? And now R, what should be R? Should be the universal gas constant divided by the molar mass of the air. So what is the gas constant? 8.314. Okay, so 10 to the 3 joules per kilomole Kelvin, no? Okay, what is M sub A? For that you should have a table. Let's find out. Thing is either at the end or at the beginning. I'm never sure about that one.
Yes, the first
Is the first table, table M1. So page down. So you go to table A1 over here. So for the air, what is the molar mass? 28.97. Okay, from table 1. So from table 1, M of air, 28.97. And what are the units? Kilogram per kilomole.
Professor?
Yeah.
Table A22, it's ideal gas property, air. Is that at 1 bar? Because it doesn't have a.
We find out. Calculate V2 and see what they give you for V2. Probably is. Okay. So now, okay, so let's do it. So let's see M sub A. So we go back to this equation, should be equal to what? So P1 is 1, 10 to the 5. To the 5 pascals. Times AV1, which is 50, cubic meter per minute, divided by 8.314 10 to the 3 joules.
Should be
But I put joules because we didn't put kilopascals. You see why?
Yes.
Otherwise we're gonna end up kilomole Kelvin divided by 28.97. What were the units for that? Kilograms.
Kilograms or.
Kilomole Kelvin. And I need to multiply this by T1, which will be 305 Kelvin. Okay, so we have a bunch of unit transformation here, no? Okay, but let's cancel whatever we can, and then you give me values, and then so these kilograms more will cancel with this one, and then that's all we have, no? Okay, if you want, we can do this one. This will be what is this? This is Newton meter square, no?
Professor, the 28.97 is kilograms per kilomole. Doesn't have a Kelvin attention.
Okay, so
the Kelvin up there and that Kelvin cancel out.
so these two cancel. Okay.
Yes.
All right. Thank you. So if you want, give me a value, and then we work out the units. 57 for all that stuff.
Yeah.
Somebody gets 57. I don't know. I just want to do the values. Okay, so 57. And now let's see what would be the crazy units we get, so that we can simplify. So we'll get newtons at the top times kilograms, no? times meters divided by what? Joules and minutes. Is that correct?
I end up getting kilograms per
But what happened to the newtons? I mean, the newtons are there.
meters is a joule. Newton meter.
Yeah, newton is a joule. I agree. So you get kilograms per minute. Yeah. So I agree with you. So 1 joule here I can write 1 joule is 1 newton meter. Okay. So this, and this cancel. And we need to get the answer in what? Oh, good. So we need to get the answer in kilogram per minute. So we're good then. It's 57. So the answer (57) kilograms per minute. Yes.
Since you have a mole and a kilomole, don't you have to multiply?
You don't have moles and kilomoles. You have kilomoles and kilomoles, no?
Yes.
Three kilomoles?
Yeah.
The units for the molar mass is kilograms per kilomole. Okay.
8.314. No, I thought it was joule per mole.
Is it mole per I don't know. What are they moles or kilomoles?
You multiplied it by 10 to the 3, so it makes it kilomoles. Or kilograms. Or whatever.
Okay. I mean, we can go check. I have to open it. So let's see what they are on the solutions. See if we open it once. 57.12. Okay. I know because we need to find. So that's for the air. Yeah. Okay. So we're good. So now that we found this term over here, what do we need to do? We need to find H1, H2, H3, and H4, no? So from where do you think we're going to get all those values? From the tables, no? So let's start maybe by H1 and H2. Hopefully we can get those ones from the table. So let's start maybe by, yeah, H1 and H2 should not matter. Let's see how they did it here, the table. They did it by table or using the equations. Table 822, okay, it's faster using the tables. Okay. So, if we come over here, you should have a table for the air. So, 822. See if I can get there. A6. Oops. What is this? 823. So, 822. So here they are doing an assumption. So let's see what they're doing. So this is okay. So over here, what is the temperature at 1? 305. So what should be the H? So let's say from table 822. At T equals 305 Kelvin, we have H1 equal to 305.22. So I'll show you what I did. Okay, basically this is what I've done. Okay, but I'm sure they did that assumption here. Let's see what I've done. So yeah, 290. Okay, and what is the temperature at T2 is 295, which is 295.17. Okay, but here comes my question to you guys. They are doing one assumption. What is the assumption they are doing over here? Look at the figure. That they are at the same pressure. Is that really true? Almost, but not quite, no? Okay, so basically that table is probably at atmospheric pressure, which will be the P equals to 1 bar, no? Yeah? Okay, so just want to point out that, no? Because they only have in function of the temperature. So we have here, so we can say, so I can say here P2, so assuming P2 almost equal to P1 at T equals, what was the temperature? 295 Kelvin. H2 is equal to what? 295.17, no? 295.17. Okay, and the units of this should be kilojoules per kilogram. Yeah, okay. All right, so we have this. Okay, now for H3, and H4, so for H3 and H4, what is the substance? Refrigerant, no? So what is the table? I think it was table A11, if I remember from the solution. Is it A11? Oh no, go. A11. Okay, so A10 is this, so I guess A11 must be saturated. So basically, what do we know about? So you need to go to your figure. So A3 is what? Oh, so let's start by H3. So H3 is actually a mixture, no?
Yes.
So it's probably going to be A10, I guess, no? I don't know, well, let's go. So A3 is a mixture. So we know 5 bars and 0.2. So let's see. 5 bars. So let's go to this one over here. No, it's this one. A11 at 5 bars. So from table A11 at P equals 5. Then what do you need to know? We need to find what is V fluid and V gas, no? Because it's a mixture at 3. So in order to find H, so we need to find not the V but the H, sorry. We need to find the H, those 3 values we need. You can just put this one. This one, really guys, if you want to save time, this one is just the difference between this one minus this value. Okay? So let's say from table A5 we have H fluid equals to 71.33. H gas equal to 256.07, and we know that X3 was equal to what? 20% of 0.2. So let me go back to the page. So basically what do we have? H3 over here will be equal to what? H fluid plus X3 H gas minus H fluid. I mean, I can look at the solution, okay, to save some time, maybe, since we have it. So let's see, H3 looks like it's going to be 108.28. Okay, 108 point, I don't, 108.28. Okay. Okay, and I mean, I don't want to rush it, but then what we need to do? We need to do is to find H4, no? And we go and substitute into, where's that equation? Where's that equation? We have this one. Then we need to find H4, and we substitute into this equation. We find N sub R. Okay? So we finish that next time. But in here, Q, they ask us to find Q. So what is this Q over here? What is this Q? So it's the basically is you see the air is being cooled, no? Okay? But probably the P3 over here, but the refrigerant is probably being heated, no? Okay? So here you have two ways to do it. It should be equal. So the amount of energy, the Q, so the air, what's going to happen to the air? The air is going to lose some Q, no? Some heat, correct? But the refrigerant is going to gain some heat, correct? So the amount of heat gained by one is equal to the amount of heat lost by the other one, no? So we can either try to find out what is the amount of heat gained by the refrigerant, or try to find out what is the amount of heat lost by the air, no? And those two should be equal. Okay, so we'll do that next time. So just one thing, I'm going to give you a homework for next Thursday. So Tuesday we finish this, and if you have questions about the homework, I can answer the questions, okay?
Do you read like starting problems or you put them on later?
I'm going to put them online.